Welcome back. This is the second lesson recording for IM2, October 19th, 2020. So now we're going to go on to a decimals exercise, and with the link that is provided on Canvas, you are going to complete card number 1 to 10 all the way. The first 6 cards will talk about organizing our understanding of the first of the two concepts, the congruence versus similarity. And then 7 to 10, we're going to be doing some critical thinking of similarity. So please pause the video and complete those cards first. I'm quickly going to go over the answers. The first card, okay, congruence versus similarity. What do you know? Looking at these two figures, are they congruent or similar? This is congruent, right? What about these two figures? Well, they're same shape, but they're different size, so this is similar. Okay, that's what we mean by congruent and similar. Now, congruence versus similarity transformation definition. Transformation that can be used to show two polygons are congruent include list all possible transformations. And those will be translation, rotation, and reflection. Okay? And I can share that with my class. And then the transformation that can be used to show two polygons are similar. Okay, for similarity though, we have the same transformation, translation, rotation, and reflection as the congruence, but on top of that, we need to dilate it. Okay, we need to make it bigger or smaller. So there is additional translation or transformation that is required or is allowed for similar figures. Okay, and then next question card said, two polygons are congruent if all corresponding angles are what? The corresponding angles have to be congruent. And what about the corresponding sides? They also have to be congruent. Okay, what about similar triangles? All corresponding angles are congruent. Okay, but all corresponding sides they do not have to be congruent. They just need to be proportional. That means the ratio between the corresponding sides have to be exactly the same, right? Or the scale factor has to be the same for each of the corresponding sides. Okay, the notation used to indicate congruence is, the congruence would look like this. That's the notation, while a similarity would look like that. Okay? Triangle shortcuts. When the polygons are triangles, we can use shortcuts to test if they're congruent. The valid shortcuts to test triangle congruence are, okay, for congruence, it's SSS, SAS, ASA, AAS, and HL. Notice that ASS is not a congruence shortcut. Similarity shortcuts are SSS, just like the congruence, SAS, just like the congruence, but ASA and AAS, they are both covered by just two angles. Okay, because we just need the angles to be congruent. So if you have two pairs of congruent angles, then we know that the third has to be congruent as well. And at that point, we don't really care about the third side. Okay? So, and HL is also triangle similarity shortcut as well. And finally, if two polygons are similar, they are congruent. If two polygons are congruent, they are similar. Okay? True or false? If two polygons are similar, are they congruent? Not necessarily. Okay? They have the same angles, corresponding angles, but the side length are different, or side length may be different. So it's false. Okay? If two polygons are congruent, then they are similar. Well, if they have the same corresponding angles, then yeah, they are similar. Okay? The congruent polygons have the scale factor of 1. So they are similar, but their scale factor is just 1. So it's true. Okay, then card number 7. Decide if two isosceles triangles are similar, sometimes, always, or never. If sometimes or never, sketch the drawings to demonstrate. So we're trying to come up with counterexamples. Okay, so look at this triangle. So I can have this triangle. Okay, it's not a very nice triangle, but let's say this is an isosceles triangle. Okay, now is this triangle and this triangle, okay, these two triangles are both isosceles triangle. Do they look similar to you? No, they do not. Okay, so this is definitely not. Okay, can you have some isosceles triangle that are similar? Yes, you can sometimes, if I just make the side length to be exactly the same, and if I have the angles to be the same. So if I have this triangle, okay, if the two angles are exactly the same, then even though the two side lengths are different, then these two triangles are similar. So this is just going to be sometimes. Okay, so this is just sometimes. Sometimes it can be similar. Okay. All right, decide if two rhombuses are similar, sometimes, always, or never. If sometimes, never, or never, sketch diagrams to demonstrate. Let's see if you can draw two rhombuses that are not similar. Okay, so if I draw a rhombus like this, and if I draw a rhombus like this, so they have different side length. Okay, but if I said that the angles are exactly the same, okay, the corresponding angles are exactly the same, then they are similar. Okay, but can you also have a rhombus that is not similar? Okay, so classic example is I can just draw a square, and I know that that's a rhombus. Squares are always rhombus. Okay, definition of rhombus is that four sides, it's a quadrilateral with four sides that are same length. And if I say that is just a square, they are both rhombi or rhombuses, but they're obviously not similar. Okay, so this is going to be only sometimes again. Let's try. Decide if two equilateral triangles are similar, sometimes, always, or never. Okay, so if I have equilateral triangle, that means each of the side is equal. That also means that each of the angles, remember, because they are opposite, they have to be equal. So that has to be 60 degrees, 60 degrees, and 60 degrees. Okay? If I drew a bigger equilateral triangle, again, because the length has to be the same, that means you are also going to have 60 degrees, 60 degrees, and 60 degrees here. Because by definition, the angle opposite the identical length size, they have to be the same. And so 180 degree has to make up the triangle, so they each have to be 60 degrees each. But look at that, okay? So you have two pairs of corresponding angles that are congruent. That means by AA similarity, they are always going to be similar. Okay? Okay, so we're going to talk about the Unit 3 and 4 test that you're going to be doing on Thursday. So the congruence is covered in Unit 3, and the similarity we covered, this actually is supposed to be from Unit 4. That is why it's Unit 3 and 4. So what's going to be on is the polygon and triangle identifying shapes to be congruent or similar, using symbols and notations, writing and using statements, and using property to solve for sides and angles. And there will also be a few of the Unit 2 topics that we did not test you on in the previous test. So that's going to be the angle pairs, like the parallel line angles and linear vertical angles, and then triangle side and angle relationship. Do you remember which is the shortest, which is the longest, as well as triangle side length inequality, which means that what is the maximum length? If you are given two sides, what is the maximum length that the third side could be, or what is the minimum length for it to be able to form a triangle? And also using Pythagorean theorem, this is actually a revision from IM1. We did not actually cover it explicitly, but it is something that you should know. Alright, so things to do for studying. So do the review packet. That's going to be your homework for today, okay? I am going to expect you to turn in at least 1 hour's worth of problems. And don't just choose problems that you know how to do. Choose the problems that you do not know how to do to make sure that you do know how to solve them. And I will have the answer keys available for you by Wednesday morning, okay? So, and look at previous quiz and unit tests. So I have made all the past unit tests and quizzes open for you to view your answers as well as what you got wrong. You should be looking to see why did I get them wrong? What was my mistake? Because chances are you're probably going to make the same mistakes unless you realize what you did wrong. Okay, and then look at the class slides. They are available in Canvas lesson resources for each of the lessons. There are the slide deck as well as lesson recordings. Look at take notes in notebook. So hopefully whenever you saw the take notes symbol, you've been taking notes. Okay, that will be all definitions, formula, examples, and look for comments from the homework. So you should definitely be doing that because that's going to be addressing some of the common mistakes. So I am going to hold an extra study hall. That's going to be on Wednesday 2 to 3 or by appointment. Alright, so let's quickly just go over some of the common transformation rules. These are the rules. And if you do not have these down, you should pause the video and write this down. And put a box around it so that it's easy for you to find, so that you are not flicking through your notebook trying to find these formulas, because you're going to need them for your test. Using transformation rules. So knowing those rules, if triangle ABC is defined by these points, which triangle below is the image of triangle ABC when it's rotated 90 degrees counterwise about the origin. Okay, so how do I do this? Okay, so I need to go back to the formula. Okay, so we are rotating counterclockwise 90 degrees. So what happens to rotation? The x and y, they swap, don't they? It becomes, instead of x and y, the values swap. Y, it becomes y and x. So they swap in value, as well as the y value takes on the negative version of it. So let's look at this problem. So x and y swap, but the y is going to take the negative version of it. So it's not going to be 2, but it's going to be negative 2, 3. So negative 2, 3, like this. Okay? And this one, likewise here, it's going to be 9 and 4 here, 9 and 4, but 9 is going to be negative 9 and 4. And then 6 and 7, instead of 6 and 7, it will be 7 and 6, 7, 6, and 7 will be negative 7, 6. So it will be A will be the correct answer. Alright, recognizing transformation rule. So if you see these numbers, 3, 4 became 3, negative 4. Which is the transformation that fits in with this? Okay, how are the coordinates changing? The x stays the same, but the y coordinate flips inside. So look for the rule, and that's the reflection across x-axis. I'll continue in the next